share my screen?
Just one
No,
second.
no.
Let me have the
Okay.
pleasure. Let me have the pleasure of introducing
Ji, ma'am.
you along with Dr. Bindal. So,
Yeah.
as you know, Dr. Saxena, we have started this learning physics with conceptual and problem-based approach, where we organized by the National Academy of Sciences, India, NASI, Delhi chapter, which is a 10-week course started on 27th of July every evening at from between the time period of 5 to 8 p.m. And this is also available on the YouTube channel of NASI Delhi chapter. And today's subject, as has been already announced by me, is statistical mechanics. And yourself, Dr. Aditya Saxena, has been working in Deshbandhu College, University of Delhi. Dr. Aditya Saxena is an assistant professor in the Department of Physics of this college, and he has over 16 years of research, 16 years of teaching experience and also research experience. He has published over 20 research papers in international refereed journals and has presented papers in international and national conferences. He has been awarded the Best Innovations Award in 2015 by University of Delhi, and he has been a member of numerous committees of UGC, CEC, and other academic institutions of our country. He has also been the head Department of Physics and the Dean School of Physical and Mathematical Sciences at Central University of Haryana. So I, along with my co-convener, Dr. Pushpa Bindal, and my organizing team, we welcome you very much, Dr. Aditya Saxena, Dr. Pushpa Bindal.
Yeah, Dr. Saxena, welcome you. We are looking forward to your talk, and I'm sure you're going to illuminate the students with your knowledge of statistical mechanics, and they are going to enjoy your talk.
Ma'am, your video is off.
My video has to be enabled by somebody. It is muted.
Yeah, just ma'am, just a time lag, delay in time. It's done.
Okay.
And now you can please, yeah.
No, I have enabled it now.
Exactly.
So a very hearty welcome to Dr. Saxena. And I have had the pleasure of working with him for ILLL. And I welcome you, Dr. Saxena. And we are all, along with the students, looking forward to your lecture on statistical mechanics. A very warm welcome to you. So I invite you to start your talk.
Yes.
Please share your screen.
Yes, ma'am.
Yeah.
So thank you so much, Punita ma'am and Pushpa ma'am, for giving me such a nice introduction. And today I'll be discussing the three statistics, among the basics of the three statistics, that is the Maxwell-Boltzmann statistics, the Fermi-Dirac statistics, and the Bose-Einstein statistics. So I would begin by sharing my screen. I hope my screen is visible.
Yes, it is visible.
Yes, visible.
Yeah, so I hope my presentation is also visible.
Yes, it is visible. Please go to the screen slideshow mode.
All right.
So view in the slideshow mode. It is stopped sharing.
Ma'am, I'll just share it again. Yes.
In fact, as you were a little bit delayed in joining with us, I was just briefing the students that with statistical mechanics, one should go in a graded level from a beginner's book of statistical mechanics, like Concepts of Modern Physics by Weiser, and then slowly move ahead. Well, that was the only thing I could impart to them till now. So
Yes.
when you finish, please do suggest some books, which will also be given to them as a list. So please share your screen. And
yes, ma'am. Just a minute.
Dr. Saxena is going to touch upon a subject which is intricate in statistical mechanics, that is a bifurcation of statistical mechanics into three categories: Maxwell-Boltzmann, Bose-Einstein, and Fermi-Dirac statistics. And he will be telling you how to recognize which statistics is to be applied and so on. Can you go to the slideshow mode, or is it a problem?
Ma'am, I think I'll just see if, because I think that slideshow is somehow, it's again, then I'll just see if it works, it's fine. Otherwise, I'll continue like this only. So I'll just try the slideshow.
Or you can just maximize the size of the slide, because because
Yeah,
maximize
so
the
I
size.
think that will be better. I think that will be better. I'll just increase the
Okay,
size.
it doesn't matter. I mean,
Uh,
because students who are viewing it on the phone find it too small. If you keep
Ma'am,
it,
I'll just see if the slideshow works. I'll just see. Yeah, I
yeah,
think now it's working.
it
Okay,
takes a
ma'am.
time lag. Yeah,
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 yeah.
yeah.
Here it is.
It's
Here it
fine
is.
now.
Here it is.
Absolutely.
We have very patient listeners and very patient and very good students in our audience, Dr. Saxena. They understand
Yeah.
that
So
network issues and delay times are a parameter in learning in these corona period. So please welcome. Yeah,
yes,
please continue. Thank you so
yes,
much.
ma'am. Good evening, students. Today I'll be discussing. In fact, I'll be starting my discussion because I'll be taking this discussion into some of the future sessions also. But what I'll be doing today is basically try to give you the basic feel and introduction to the three statistics. And my primary motive would be to actually familiarize all of you with the way how we place the particles in the various energy levels, how the filling or the populating of the various energy levels happens under the three statistics. So what I'll do is that I'll start my talk with an introduction to what these three statistics are. So first of all, the Maxwell-Boltzmann statistics. So this basically applies to identical but distinguishable particles of any spin, for example, molecules of gas at room temperature. Then we have the Bose-Einstein statistics. This applies to identical and indistinguishable particles. So the one basic difference that comes between Maxwell-Boltzmann statistics and the Bose-Einstein statistics is that in case of Maxwell-Boltzmann statistics, the particles are distinguishable. But in case of Bose-Einstein statistics, the particles are indistinguishable. And these are particles of zero or integral spin, and they are called bosons. And the example is, let's say, hydrogen gas or either gas of hydrogen atoms at very low temperature. Then the third type of statistics is the Fermi-Dirac statistics. This again applies to identical and indistinguishable particles of half integral spin, which obey Pauli's exclusion principle, and the particles are called fermions. And one of the very typical examples of this is the electron gas in metals. So now, first of all, why do we need three statistics to begin with? We have a collection of particles. Since the particles are very large, so we could have very well done with one statistics. So the first question that obviously comes to our mind is that why do we in the first place need three statistics to deal with a very large collection of particles when seemingly all the three, when seemingly, the particles appear to be like you can explain it through any simple statistics. So So what I would like to draw your attention to is some of the things that I'm sure a lot of you would be knowing, but I'm not very sure how many of you would have thought about it that way. So we all know that at STP, that is at standard temperature pressure, which is room temperature. So if you take the room temperature to be 298 Kelvin or 300 Kelvin, and pressure is 1 atmosphere, that is the normal pressure that we have over here. So 1 mole of gas contains 6.023 into 10 to the power 23 atoms, which is your Avogadro number. And this 1 mole of gas occupies a volume of 22.4 liters, which if you convert into meter cube, this works out to 22.4 into 10 to the power minus 3 meter cube of volume. So this is the amount of volume that a 1 mole of gas at STP occupies. So if you do a simple calculation and you find out the number density, so you have the 6.023 into 10 to the power 23 atoms, which is occupying 22.4 liters or 22.4 into 10 to the power minus 3 meter cube of volume. So your number density works out to 2.69 into 10 to the power 25 atoms per meter cube. All right. And if you do a reverse calculation, that what is the volume that each atom would occupy, or rather what is the volume that is available. Now here I'm not saying the volume that each atom would occupy, What I'm talking about is the volume that is available to each atom at STP, that is at 300 Kelvin temperature and 1 atmospheric pressure. So the volume that is available to each atom at STP is 3.72 into 10 to the power minus 26 meter cube. So this is the volume that is available to each atom. Now, if you look at, I mean, right now, because we are not really getting the quantum mechanics or the quantum statistics into the picture. So typically just speaking about classical calculations. So we know that classically the roughly the radius of an atom is 10 to the power minus 10 meters. So I mean, if you do a very crude calculation, I'm not taking the 4/3 pi r cube, so assuming that the atom is spherical in shape and all that, but doing a very, very crude calculation. So the approximate volume that an atom would occupy classically is 10 to the power minus of the order of 10 to the power minus 30 meter cube. Now, if you were to compare this volume, right? If you were to compare this volume with the volume that is available to each atom. So this is the approximate volume that an atom would occupy. And this is the volume that is available to an atom. So if you find out the ratio of these two volumes, that is the volume available to an atom to the volume of an atom, the ratio is of the order of 10 to the power 4, right? That means that an atom roughly has 10 to the power 4 times the volume available for it to be there. Now, this is a very, very important figure. And why is this very important? This is very important because what this actually tells us is that at room temperature, this the volume that is available to an atom is 10 to the power 4 times its own volume. In other words, at room temperature, the atoms are very sparsely distributed. And just to put things in perspective, because so that we exactly understand what we are wanting to say, supposing if we consider a human being, so a human being roughly measuring 1.5 meters in height. So basically what this means is that if we were to take a similar collection of human beings as we have taken in case of the atoms at STP, that is the gas, normal gas that we are all moving in, then the chance of a human being coming across another human being is extremely small. Reason being that if the average height of a human being is around 1.5 meters, then a human being typically will have around, almost 10 or more than 10 kilometers of distance available to it. And so that because basically it's something like 10,000 cubic kilometers of volume that will be available to it. So something like maybe 10, maybe 50 or 60 or whatever, 20 kilometers. So that is the kind of distance that it will have to traverse before it comes across another human being. So what I'm just trying to say is that if supposing we were so sparsely distributed that before we could interact with another human being, we would have to travel something like almost 30, 40 kilometers, right? So, or maybe 20, 25 kilometers. So imagine how difficult it would be for us to communicate. So in a similar manner, when we are talking of any collection of gaseous molecules at room temperature, then given these parameters that we've just seen, what we realize is the atoms are so far apart. They are so far apart from each other that it is actually possible to individually track the trajectory of the atom. So even though the atoms are identical, okay, because if I go back to my previous slide, where I said that in case of Maxwell-Boltzmann statistics, the atoms or the particles are identical but distinguishable. So why are they distinguishable? The reason why they are distinguishable is because they are so far apart that even though these particles are identical, yet because they are spaced out so much, so it is possible to track the trajectory of individual particles, all right? And because it is possible to track the trajectory of individual particles, hence we can say that all the particles are distinguishable. And because the particles are distinguishable, therefore, when we are stacking up these particles in different energy levels, it gives us a particular kind of statistics, which we call as the Maxwell-Boltzmann statistics. Okay. Now, so like I said, that the size of the atom is much smaller than the interparticle separation. Hence, the atoms particles are distinguishable since they are very far apart and their trajectories can be traced individually. Now, what happens that, I mean, so, okay, so far so good. We are all at room temperature. We are all, doing pretty well. So Maxwell-Boltzmann statistics appears to be very good for us. And in fact, it is very good for us when we are dealing with normal temperature pressure or standard temperature pressure. But where does the difficulty come in? Okay, now the difficulty comes in when the particles are no longer distinguishable. Because the key or the most important part about the Maxwell-Boltzmann statistics was the distinguishability of particles. So now when the particles are not distinguishable, so then the next question that obviously comes to mind is that when would the particles not be distinguishable? So let us look at the two conditions which are typically put, which actually brings in the quantum mechanics or the quantum statistics into play. So for the two conditions for the quantum nature to become significant are, one, that lambda thermal, that is the thermal de Broglie wavelength, is greater than or equal to twice the interparticle separation. All right. So where the lambda thermal, that is the thermal de Broglie wavelength, is given by the relation. So typically, if you look at the de Broglie wave nature, wave particle duality. So what the relation that de Broglie gave was that lambda is equal to h by p, where h is the Planck's constant and p is the momentum of the particle. So and this, if you do again doing a very simple calculation. So if you put the momentum, I mean, if you take the momentum as mass into velocity, and we are all doing this classically, so taking the momentum to be mass into velocity. So your energy, kinetic energy, becomes half mv square. And if you substitute for that, then your momentum in terms of energy can be written as under root twice mass into the energy. So from that, you can see that your lambda thermal, so this is the relation that you should get for lambda thermal, not taking into account some constants and all. So actually the value of the thermal de Broglie wavelength comes out to be h by 2 pi m kBt, where the factor of 2 and m is same from here. This pi actually comes about as a factor that is introduced to simplify the equation. And this kBt is basically the energy. So all of us know that if you look at kinetic theory of gases, and I mean, again, right now we are just talking about classical this thing. So from kinetic theory of gases, you know that half kBt is the energy per degree of freedom that is available to a gaseous atom or molecule. So half kBt, and if it's a, I mean, if it's a three-dimensional this thing, then you half into the 3 degrees of freedom due to the 3 dimensional, 3 by 2 kBt is what you get. So I mean, doing all of that calculation, so finally the value that you get for thermal de Broglie wavelength is h by under root of 2 pi m kBt, where h is the Planck's constant and other constants we've already discussed, and kb is the Boltzmann constant. So now here there is another important and interesting aspect to this equation. If you, in this equation, lambda thermal is h by p, if you take p on this side, so h is actually approximately equal to lambda thermal into p. And why this relation becomes important is because that the moment you start going into the quantum regime. So when I'm saying that you start going into the quantum regime, what do I mean? Now, all of us know from the uncertainty principle, the Heisenberg's uncertainty principle, that delta x delta px is h cross by 2 is greater than equal to h cross by 2. That means that the minimum uncertainty in determining the position and the momentum of a particle simultaneously has to be greater than or equal to h cross by 2. All right. So from that concept, basically that delta x gives us the minimum extension or the minimum spatial extension or extent in which the particle will exist, and we cannot further reduce that minimum spatial extension because that will violate the uncertainty principle. So in other words, what one is trying to say is that from this relation, what one can see is that this lambda thermal actually gives you the extent of the wavelength associated with a particle at a particular temperature. And that wavelength will give you the extent, the spatial extent of the wave of that particle. And we know that when you talk of a wave, so basically if you look at the wave function, the square of the modulus of the wave function gives you the probability density of finding that particle. So in other words, whenever we are talking of a wavelength, what we are actually saying is that any particle who has a wave nature associated with it, the thermal de Broglie wavelength will give the extent or the minimum spread in which the particle would exist at a particular temperature T. And now when this thermal de Broglie wavelength becomes greater than or equal to the interparticle separation. So now please, again, I would like to, take your attention back to what
So kindly unmute. Yes. Fine, sir. Please continue, sir.
So, so if we again look at this, the classical picture that we were just discussing. So over there, what we saw was that the interparticle separation was much, much larger than the size of the particle, right? But when we talk of a situation where the thermal de Broglie wavelength, which is now again giving us typically the extension, spatial extension, or the minimum spread in which the particle must exist, then what we see is that if this extension becomes comparable to the interparticle separation, which means that the wavelength or the wave is overlapping, the wave functions of the two particles start overlapping, right? Or the wavelength of the two particles start overlapping, then what will happen? Because all the results of Maxwell-Boltzmann statistics work extremely well so long as the particles are very far apart and they are in a classical regime. But the moment the interparticle separation becomes less than or equal to the thermal de Broglie wavelength, this entire thing changes, because now the quantum nature of the particles becomes significant. And so this is the first condition. The second condition is that the product of the number density and the cube of the thermal de Broglie wavelength should be greater than or equal to 1. So now again, since the thermal de Broglie wavelength is a measure of the spatial extension of the particle or the wave packet associated with the particle, hence its cube gives us the volume, typically the volume extension in which the particle must exist. So this volume extension in which the particle must exist, the product of this with the number density, this should be greater than or equal to 1. Now compare this with, if again I would like to go back to the this slide, if you were to take a product of this number density, this and this volume. So if you take a product of these two, your typically the order of this n into this volume v, the small n times this volume v would come out to be something like 10 to the power minus of the order of 10 to the power minus 5, right? 2.69 into 10 to the power minus 5. This is the order that you have when you're talking of a classical particle or a particle which is obeying the Maxwell-Boltzmann statistics. But compare this result, which is of the order of 10 to the power minus 5, with this result, where the number density times the spatial volume available to the particle is greater than or equal to 1. So what does this signify? This basically signifies that the volume that is available to the particle has now become less than the volume occupied by the particle. And this classically one cannot imagine. Reason being that classically we assume, the most or the simplest example that we take to explain atoms classically is hard billiard balls. So in case of hard billiard balls, we know that if you put two billiard balls together, you can't, beyond their point of contact, you can't press them any further. But so this is classically, but in quantum mechanics, you know that there are no hard boundaries. So there, what happens is that the extent of the wave function can overlap over many particles. The extent of the wave function of one particle can overlap over many particles without really coming in conflict with the other particle. So when this kind of a situation is there, that one single wave function is extending over many particles, which is basically denoted by this condition over here, right? N lambda thermal cube is greater than or equal to 1. And in fact, this is also, if you use the definition of lambda thermal over here, so if you put this as H by P, right? So this actually also kind of gives you the phase space density, okay? So in this manner, so when the phase space density or when this becomes greater than 1, then what happens is that the classical mechanics or the classical statistics, which is denoted by the Maxwell-Boltzmann statistics, that is no longer applicable, and your quantum statistics becomes significant. And there, once your quantum statistics becomes significant, two important things happen, which are not there, which you do not consider in the classical statistics. First, that the particles are no longer distinguishable, but they become indistinguishable. The reason being that to begin with, the particles were identical, but because in case of Maxwell-Boltzmann statistics, since they were so far apart, so you could still individually track the trajectory of the particles. But in case when you come to the quantum regime, then since the particles are so close and since they are overlapping, so it becomes very difficult to find out which particle has gone where. Okay, because they are identical particles. So, and when they are so close together, so one cannot really track how the trajectory of a particular particle has progressed or how the particles have moved from one energy level to another. So that is the first major significant change that happens when you move from classical statistics to quantum statistics. The other major change that happens is that unlike Maxwell-Boltzmann statistics, where the spin of the particle did not really matter, here the spin of the particle becomes very important. And the reason being that we know that when you come to the quantum mechanics, there, if you look at the, when you start discussing the identical particles, then all of you know that you invoke the symmetry considerations and you use the symmetry operator. So the symmetry operator for half integral spin gives you a Slater determinant when you're wanting to write down the wave function of a number of particles, right? As a linear combination of the wave function of individual particles. So it gives you a Slater determinant. Whereas if the spin of the particle is 0 or integral, then the symmetry operation actually gives you an anti-Slater determinant for the wave function defining a system consisting of individual particles having individual wave functions. So that basic difference that comes because of the symmetry operation, that the symmetry operator for the case of half integral spin gives you a Slater determinant, and the symmetry operator in case of 0 or integral spin gives you an anti-Slater determinant. Because of this, the way you fill up your particles also becomes dependent on the fact that what is the spin of your system or what is the spin of the particles, right? So these two considerations become important, and that is why the moment you cross over from classical statistics to quantum statistics, not only does the indistinguishability of the particle have to be taken into consideration, also the spin of the particle has to be taken into consideration. And based on what is the spin, whether it is half integral or it is zero or integral, two separate statistics have to be used. Bose-Einstein statistics for zero or integral spin, and Fermi-Dirac statistics for the half integral spin, right? So now moving forward, so this is a figure I just thought that it will give you an idea that how classical statistics versus quantum statistics. So this is the n lambda thermal cube, and this line, this is a plot drawn between the number density n and the temperature T. So this line, this dashed line over here, if you can see this dashed line, this basically is the line which is denoting n lambda thermal cube is equal to 1. This dashed line satisfies this equation. Below this dashed line is your quantum region, and above this dashed line is your classical region. So this is the region where Maxwell-Boltzmann statistics will work very well. This is the region where you have to either use Fermi-Dirac statistics or Bose-Einstein statistics, depending upon whether the spin of the particle is half integral or zero or integral. All right. Another thing that I would like to point out over here, if you look at this, this formula for thermal de Broglie wavelength. So in this formula, what you see is that the temperature T comes in the denominator as in the power of half, that is under root T. Okay. So if I increase the temperature, my thermal de Broglie wavelength decreases, and if I decrease the temperature, my thermal de Broglie wavelength increases. So what happens is that if I go to very, very low temperatures, okay, if I go to very low temperatures, then what happens? That the thermal de Broglie wavelength will increase, and maybe I might reach this, I might satisfy this condition, because as you go on increasing thermal de Broglie wavelength, eventually this thermal de Broglie wavelength may become equal to or greater than the interparticle separation. So one thing that we need to know over here or remember over here is that this thermal de Broglie wavelength is dependent on T, rather is inversely proportional to T to the power half. So if my temperature decreases, then I'm pushing my system into the quantum regime. That is one. Secondly, if my number density increases, see again, like I said, that from this picture, my n times V was 10 to the power minus 5, right? So from 10 to the power minus 5, if I am reaching this stage where n times V, where if I'm taking this cube of the thermal de Broglie wavelength to be the approximate volume, then n times this is greater than equal to 1. So this can happen in two ways. One, if I decrease the temperature of my system, okay, then my thermal de Broglie wavelength will increase and maybe I will be able to achieve this condition. Or if my number density increases, okay, so if my number density increases, then also I will be able to achieve this condition. And this table that I've taken over here is actually something that is illustrating this very fact. So if you look at this table, you take a hydrogen gas, 2 into 10 to the power 19 centimeter cube. This is the number density, right? So this is 2 into 10 to the power 19 atoms per centimeter cube. So this is typically your normal air. Okay. And if, so when would, now at room temperature, obviously this will behave like a classical gas and hence you will use Maxwell-Boltzmann statistics. But if you take the temperature to 5 into 10 to the power minus 2 Kelvin, okay. So if you take the temperature to 5 into 10 to the power minus 2 Kelvin, then this no longer behaves like a classical gas. but starts behaving like a quantum gas. That means the n lambda thermal cube starts becoming equal to 1, okay? And your lambda thermal becomes greater than or equal to 2Rs. Similarly, liquid helium-4. All of us know that the liquid helium-4 becomes a superfluid at the transition temperature, which is 2.2 Kelvin, okay? So if your the density of liquid helium-4 is this, 2 into 10 power 22 atoms per centimeter cube, and this is your temperature, then liquid helium-4 will also behave according to the quantum statistics. All right. And similarly, another example that we encounter is electrons in metal. Now look at electrons in metal. Now one would say that, sir, in case of electrons in metals, because I mean, what we will be discussing maybe in the next sessions is that for an electron gas in metals, even at normal room temperature, they follow the Fermi-Dirac statistics. In fact, it will be discussed as an example of the Fermi-Dirac statistics. The reason for that is that if you take this as the density, 10 to the power 22 electrons per centimeter cube as the density of electron gas in metals, then at the temperature at which this condition is satisfied is 10 to the power 4 Kelvin. So it's a very high temperature. It's like 10,000 Kelvin temperature. So obviously at room temperature, electron gas in metals will follow the quantum statistics, and hence, because electrons are again spin half particles, so it follows the Fermi-Dirac statistics. All right. So this was just to give you a comparison of the classical statistics versus quantum statistics and some parameters so that you people understand that how this change in temperature and how this change in the number density actually puts the particles in this region or in this region. Okay. So now one again important point over here, and also I'll just take two simple questions over here. So that we understand what one is wanting to say. And this is that how do you know whether a system will see? So first of all, supposing if we get questions like that, we are given a system and we are given some parameters. All right. So and supposing the question asks us, how can you say that this is Maxwell-Boltzmann? I mean, this system will follow Maxwell-Boltzmann statistics or Fermi-Dirac statistics. So obviously, the first thing that you need to do is that if you have the parameters, you calculate n times lambda thermal cube, that is the number density times the cube of the thermal de Broglie wavelength, and see if it comes out to be greater than or equal to 1. That is the first thing that you need to check. The other thing that you need to check is, supposing you've checked this and you've realized that, okay, fine, this system is following Maxwell-Boltzmann statistics. If it's following Maxwell-Boltzmann statistics, then that's perfectly okay. We don't need to bother about whether the spin was integral or half integral. But supposing from that you find out that the system is following quantum statistics. Then in quantum statistics, now there are two different types of statistics: Bose-Einstein statistics and Fermi-Dirac statistics. So which of these two statistics will the system follow? So for that, in order to calculate the spin, what do we do? So we know that typically for a neutral system, the number of protons is equal to the number of electrons. So whenever you add, so if you're taking an atom, for example, so if you add the number of protons and the number of electrons, whether the number of protons is even or odd, for a neutral system, you would be adding the same number of electrons. So your overall spin that is coming because of the protons and the electrons will either be 0 or it will be some integral multiple, right? It will be some integer. So what is it that will actually tell us whether the system will behave like a fermion or a boson? So for a system to behave like a fermion, for a system to behave like a boson, that is for the spin to be 0 or integral, your number of electrons plus number of protons plus number of neutrons should be even, or simply put, your number of neutrons should be even if, please mark this carefully, if your system is neutral. But if your system is not neutral, in that case, you need to add up all the three. All right. But if your system is neutral, then even checking out the number of neutrons should suffice. So for a neutral system, if the number of neutrons is even, then it will follow Bose-Einstein statistics. If your number of neutrons is odd, it will follow Fermi-Dirac statistics. But if we are talking about a non-neutral system, then obviously you will have to add the number of electrons plus the number of protons plus the number of neutrons. If they are even, then the system will follow Bose-Einstein statistics. And if they are odd, the system will follow Fermi-Dirac statistics. And these are just two simple examples that I've taken over here. So which of the following atoms cannot exhibit Bose-Einstein condensation even in principle? So obviously Bose-Einstein condensation is a phenomena that occurs when you're doing Bose-Einstein statistics. You go below a certain critical temperature and all the bosons condense into a ground state. This phenomena is called Bose-Einstein condensation. So if you look at these four options that are given over here, so hydrogen, this is your typical hydrogen atom. So one proton and one electron, right? Mass number is also one, there is no neutron. So 1 plus 1, this is even. So this will follow, I mean, in principle, you can get a Bose-Einstein condensation over here. 4He2, so 2 protons, mass number is 4, so 2 neutrons. And because it's a neutral system, so 2 electrons, so 2 plus 2 plus 2, 6. That's also an even number. So this will also, ideally speaking, this can also be condensed and this can also achieve Bose-Einstein condensation. Sodium, 1123. So 11 protons. Then, so here, if you look at this, the mass number is 23. That means the number of neutrons is 12. And then you add up the number of electrons. All right. So if you add up the number of electrons also to this, what you get? You basically get so 11 protons plus 11 electrons plus so 11 protons plus 11 electrons plus 12 neutrons. So this is also even, right? And because this is also even, so here again you get, this will also, ideally speaking, this can achieve Bose-Einstein condensation. Okay. In all these cases, you also see here the number of neutrons was 0. Here the number of neutrons was 2. Here the number of neutrons was 12. So all these three were satisfying Bose-Einstein. I mean, they could achieve Bose-Einstein condensation. But look at this fourth example, potassium, 3019. So atomic number is 19. So number of protons is 19. Mass number is 30. So basically what it means is that the number of neutrons is 11, right? And so 19 plus number of electrons also 19, 38 plus 11 is 49. Or simply if you look at the number of neutrons, that is also odd. So this will not achieve Bose-Einstein condensation because to begin with, this is a fermionic system, right? Now let us look at another example. So which of the following is a fermion? Hydrogen atom. So, okay, hydrogen atom, you know, 1 proton, 1 electron. So 1 plus 1 is 2. So this is even number. It has no neutrons. So this is a bosonic system.
Hello, Dr. Saxena. Hello. Hello, Dr. Saxena. Can you hear me? Students, can you hear me? So, okay, so he has exit. It is a network problem. And as soon as he joins again, just 1 second, I've heard yes. You can also see that 2-3 people have written yes. If they've written yes, then we have got your message. I just wanted to know whether I'm audible. I'm audible. And we have seen that he has exited. It is because of some network issue. So I just need 1 minute to call him back. Sir's voice is low. Yes, I will ask him to increase. And just give me a minute so that he can join back again. And meanwhile, you can just just pause over and think about what is the difference between quantum statistics and classical statistics. What is the main single criterion by which you can come to know whether to use classical statistics or whether to use quantum statistics? Number one. Number two, if you have decided that yes, it is quantum statistics, then how is it that you decide whether any particular particle or a neutral entity or any gas you will decide as following Bose-Einstein or Fermi-Dirac statistics. So I just need a slight second for him to join back again, right? Just a second. So yeah, as I expected, this is just because it is a network issue, and that's not a problem. We will have patience, and meanwhile, I will answer some of the questions which are there in the question answer box, so that time is utilized in a nice way. There is an attendance link also given by Mohini to the students in the chat box. Please be careful. The attendance link is here. Please give your attendance in the form that is there in the Zoom chat box. And now, the first question, Saurav Verma. One announcement is that attendees, I request you to kindly, when you are posing a question, please use your name. Don't ask a question with anonymous attendee, or don't ask a question anonymously. You see, we're going to be together for some time learning physics together. Would you not like to see and know the convener and the co-convener? Should we also shut ourselves and talk to you anonymously, a voice coming from somewhere? That's not nice, right? So I would love to know who is attending, and therefore please from now on use your name for asking a question, posing a question. Saurav Verma asks, sir, what do we mean by spin and spin angular momentum? You see, it appears that you are probably not yet in the third year. Otherwise, you would have been introduced to the concept of spin. However, for your information and a little bit knowledge, although not detailed, because for detailed, you will have to go to the, you will have to wait for the course of atomic and molecular physics and a little bit of statistical mechanics in order to understand it. You see, in class 11 itself, you have a concept of rotational motion. You have a concept of rotational motion, and because of rotational motion, you know that there is an angular momentum. Okay, and you know that electrons have been thought of having a spin, up spin and down spin, up spin and down spin, right? And so up spin and down spin, that means you are aware of the electron spin. Now the spinning motion of the electron is associated with the angular momentum due to the spinning motion of the electron. This is in the case of an electron. You consider an electron moving around in the simplest Bohr atom model, and the new electron is moving around the nucleus, right? And then it is also spinning, just like Earth spins on its own axis and goes around the sun in a particular orbit. So the angular momentum, which is associated with the spinning motion of the electron, is called the spin angular momentum of the electron. Now we will just extrapolate our statement and apply it to any particle. Every particle has a particular spin and hence is associated with the spin angular momentum. And that spin angular momentum must be either a half integral multiple of h cross, or it should be an integral multiple of h cross. And this is what Dr. Saxena is trying to explain to you in his lecture. So Dr. Saxena is back. That's nice.
Yes,
Dr. Saxena, could you please continue sharing your screen, or you can take up some of the questions as you deem fit, as you decide.
Ma'am, I think first let me just complete the part that I was
that's
thinking.
all. I was just filling up the time of your joining by answering some of the questions. So yeah, please continue. Share your screen, and we can continue definitely. So I was just trying to answer the first question, that the spin angular momentum is an inherent property of every particle, like electron, proton, neutron, and so on. Yeah. Thank you. Yeah. Good.
Okay. So
yeah, please continue.
Yes, ma'am. So, then we were talking about beryllium. So hydrogen, helium, lithium, beryllium. So the atomic number is 4, right? And mass number is 2. So again, the atomic number is 4, and it has so basically 4 protons, 2 neutrons, and 4 electrons. So that is also a bosonic system. So this will also not be a fermion. Then deuteron. So deuteron, as you know, is a hydrogen atom, but it has 1 neutron also. So this will now have 2 plus 1, that is 3, right? So 3, because it will have an odd number, the total of the number of protons plus number of neutrons plus number of electrons. So this deuteron, this is a fermion in amongst all these 4 options. Now next, so what my next part of this talk would basically be how I will just try and understand that how the particles fill up the different energy levels. So I would be discussing that. So we've already discussed that the particles are distinguishable, and there are no symmetry restrictions, which means that spin really does not matter over here.
Dr. Saxena, could you be slightly louder or come closer to your laptop, because some students have voices problem. Somebody is having a problem, somebody is not having a problem. You could just, a little bit towards your laptop. Thank you so much. Thank you.
So now let us assume that each eigenstate of the ith quantum group may contain Ni particles. What this statement means, there is a figure which will come in one of the subsequent slides, so there we'll understand that. And what it also says that when we are considering a system, the total number of particles remains constant in that system. So n is constant over here, and which is n1 plus n2, where this n1, n2, ni, they are basically the number of particles that are associated with one particular quantum group or quantum state. So this ith quantum group, so ni particles occupy this ith quantum group. Or maybe you can say that these Ni particles occupy the ith energy level. If you, we can also look at it that way, that it is occupying the ith energy level. And so the total energy of the system is also constant. So if N1 particles occupy energy level epsilon 1, so the total energy of the particles in this is N1 times epsilon 1. Then if N2 particles occupy energy level epsilon 2, so N2 times epsilon 2, and so on. So this gives us the total energy, and this is also a constant. So now, I will again, so one is not going into the derivation, okay, but now let us just look at how these different particles will stack up. So in all, you have n particles, right? All the particles are distinguishable. So supposing if there are 2 energy levels, so if I put particle A in energy level 1 and particle B in energy level 2, and if I then put particle B in energy level 1 and particle A in energy level 2, right? So these give me 2 different distributions, okay, because the particles are distinguishable. So A in level 1 and B in level 2 is different distribution from B in level 1 and A in level 2. Also, both particles A and B can be in level 1, and both particles A and B can also be in level 2. Okay, so in this manner, so like if you're just looking at a 2-level system, so the first thing that you have is that so if there are n particles, there are n factorial ways in which you can distribute those particles. All right, now again, supposing if each of these energy levels has a degeneracy Gi. So what do I mean by this degeneracy Gi? Maybe I'll just go to this figure. So if you look at this figure, this is your energy level 1. It has N1 particles, right? And it has a cell degeneracy G1, which means that in this energy level 1, there are these G1 sub-levels. So this N1 particles can distribute in these G1 sub-levels, all right? So these N1 particles, they can distribute in G1 sublevels, but within a sublevel, supposing if you are in this particular sublevel, then because the particles are identical, so within a sublevel, so within a particular degenerate state, there you cannot distinguish how the particles came in, right? I mean, how the particles are stacked. But even within an energy level, okay, in each of these degenerate states, how the particles are occupying, that each distribution is a different distribution, because all the particles are distinguishable. All right. So coming back to this, so now for a particular energy level I, if Gi is the degeneracy, all right, then the number of ways in which Gi degenerate states can be occupied by Ni particles is given by Gi to the power Ni. Okay.
Dr. Aditya, because of your
And
network, Dr.
within,
Aditya,
yes, ma'am. Yeah, ma'am.
because
Am I
of
audible now?
yes, but because of the bandwidth requirements, it will be smoother if you close your video and let just only the audio on.
Okay, ma'am. I'll do that, ma'am. I'll
Yeah,
do that.
then this breaking voice will become better.
Okay, ma'am. So, so within, because within the you know within the this degenerate energy level, how the particles are coming in, that will not lead to any new distribution. Okay. So there are Ni factorial ways in which each of these Gi degenerate levels can be occupied by Ni particles. So this does not lead to any new distribution. So so if I want to really find out my the total number of different distributions or thermodynamic probability of total n particles with the ith state having Ni particles, each particle having energy epsilon I, and Gi be its statistical weight or the degeneracy, then Gi to the power Ni, n factorial times Gi to the power Ni upon Ni factorial is the total number of different distributions of thermodynamic probability of that particular degenerate state. And that because this is for one energy level, and that over all the energy levels, so you simply take the multiplication over all the energy levels. So this gives you the total thermodynamic probability, okay, or the total number of different ways in which the different distribution can be done, right? And then using this definition and the conditions that we had imposed earlier, that the total number of particles is constant and the total energy is constant. So then you do some mathematics basically, and you introduce the concept of Lagrange's undetermined multipliers, and you solve that. So finally you get a distribution which is the Maxwell-Boltzmann distribution function Ni is equal to Gi upon e to the power alpha plus beta I, where alpha and beta are the Lagrange's multipliers, undetermined multipliers. And this we shall see maybe in one of the subsequent sessions, that this beta is basically 1 upon kbt, where kb is the Boltzmann constant. And alpha is mu upon kbt, and so basically this is beta epsilon I. So this is how that distribution function comes about. So this is for Maxwell-Boltzmann statistics. Now, yes. Now, when you come to the Bose-Einstein statistics, what happens is now the particles are indistinguishable, right? Even though, these particles basically follow the, since they're following the Bose-Einstein statistics, so your spin is either 0 or integral. Because integral, therefore, the particles do not obey the Pauli's exclusion principle. In other words, what I'm trying to say is that you can stack any number of particles in a particular energy level, all right? So each eigenstate of the ith quantum group may contain Ni particles. The total number of particles is constant. Again, that same condition that we discussed even for Maxwell-Boltzmann statistics. Now here what happens is that you have, because here the particles are indistinguishable. So if you can just recollect that example that I had taken, that if you have particle A in level 1 and particle B in level 2, and if you interchange, that is particle B comes to level 1 and particle A goes to level 2, then in case of Maxwell-Boltzmann statistics, that led to two different distributions. But in case of Bose-Einstein statistics, because the particles are indistinguishable, therefore you can't really label them as particle A and B. So long as one particle is in level 1 and one particle is in level 2, it is one distribution, and interchanging the particles will not lead to a new distribution. All right. So basically, you know that there are for the ith energy level, the degeneracy is Gi. So basically, you have Gi different degenerate energy levels or sublevels within that ith energy level. The total number of particles in the ith energy level is Ni. All right. So the total number of different ways in which Ni particles can be distributed in Gi cells. So if you take one particle and then you put it in one cell, and then so the remaining cells is Gi minus 1. All right. So if you do that, I mean, again, this is all mathematics, but if you do that, what you realize is that Ni plus Gi minus 1 factorial is the number of ways in which you can distribute Ni particles in Gi cells. Also, these Ni particles, because they are identical, so their interchange amongst themselves does not lead to any new distribution. So this is Ni factorial. Also, the supposing you put one particle in one of the degenerate energy levels, so your remaining degenerate energy levels is Gi minus 1, and these remaining energy levels, so the next particle is again free to occupy any of these levels, so that also will not lead to any new distribution. So this is Gi minus 1 factorial ways in which you can place this. So these Ni particles arranged amongst themselves, that is n factorial ways in which they can be arranged, this will not lead to a new distribution. And similarly, these Gi minus 1 factorial, that is the way in which if you one particle has occupied one particular degenerate level and the remaining G minus 1 degenerate levels are available, so putting a particle in any of these will again not lead to a new distribution. So your total distribution for the ith level comes out to be Ni plus Gi minus 1 factorial upon Ni factorial times Gi minus 1 factorial. And this is for one particular degenerate level, and this multiplied over all the so this is this is for one particular level, for one particular energy level, which has a degeneracy Gi and total number of particles Ni. Now this when you want to find out the total number of different distributions or the thermodynamic probability, right, then this multiplied over all energy levels, so multiplication over I, this will give you the total thermodynamic probability. And the distribution function, again, you use mathematics and you use the method of Lagrange's undetermined multiplier. You can do that also. You can also find out the distribution function by using the concept of partition functions. So, I mean, you can do both the ways. You can use the concept of Lagrange's method of undetermined multipliers also. You can also use the concept of partition function, and then you do the grand partition function, and then from that also you can find out. So the distribution function for Bose-Einstein statistics comes out to be Gi upon e to the power alpha plus beta epsilon I minus 1. Actually, that epsilon is missing over here. It should have been alpha plus beta epsilon I. So epsilon is the energy of that particle. So this is the distribution function. Now coming to Fermi-Dirac statistics, like we have discussed earlier also, in case of Fermi-Dirac statistics, these are the particles which have half integral spin, and because these are particles with half integral spin, therefore so these particles are also indistinguishable, because this is again in quantum regime, so these are indistinguishable, and so there is no distinction in the number of ways in which Ni particles can be chosen. But because these are particles with half integral spin, so therefore they obey Pauli's exclusion principle. All right. And because they obey Pauli's exclusion principle, therefore one particular degenerate sublevel. Okay. So if you have the ith energy level and Gi is the degeneracy, that means this ith energy level is, again, let me just take this figure. So if this is the ith energy level, this ith energy level is divided into Gi degenerate energy levels, and total number of particles that are there is Ni. So in case of Fermi-Dirac statistics, because we know that each particle can only occupy one energy level according to Pauli's exclusion principle, that no two electrons or no two fermions can have all the four quantum numbers same, right? So basically one fermion can occupy, so one energy state can at the maximum be occupied by only one fermion. So each of these GI degenerate states, they can either be empty, that is there is no particle in them, no fermion in them, or they can at the maximum have or accommodate only one fermion. Okay, so this is in case of Fermi-Dirac statistics. And so if you do this, so basically the total number of ways in which, because these particles are indistinguishable, so the total number of, if you have Ni particles, so the total number of ways in which these Ni particles can occupy GI states is, so if one particle goes into the first particle, if you look at the first particle, there are GI ways in which you can place it. Then if you go to the second particle, now there are GI minus 1 ways in which you can place it. If you go to the third particle, then GI minus 2 ways. So in this way, you see that basically there are GI factorial ways in which Ni particles can be placed. However, again, because the particles are indistinguishable, so the way in which you choose the particles, right, the order in which these Ni particles were chosen, that order in itself does not really matter. So that there are n factorial ways in which you can choose that order. So these n factorial ways will not lead to any new distribution. So you divide by n factorial, Ni factorial over here. Also, because out of these GI degenerate energy levels, only Ni degenerate levels are occupied. Okay, so the remaining GI minus Ni degenerate energy levels are all empty, and because they are all empty, hence amongst themselves they also do not lead to any new distribution. Okay, so in this manner, if you then for one particular energy state, ith energy state, the total number of different distributions or thermodynamic probability for the ith state is GI factorial upon Ni factorial times GI minus Ni factorial. And when you do this, when you want to find out the thermodynamic probability or the total number of different distributions for the entire system, so going over all the levels, then you simply again take the multiplication over all the levels. So this is your final total number of different distributions or thermodynamic probability for an n particles, with the ith state having Ni particles, each particle with energy epsilon I, and GI be its statistical weight or the degeneracy. And the Fermi-Dirac distribution function again is given by Ni is GI e per alpha plus beta epsilon I plus 1. Again, I would like to mention over here that this distribution function is basically mathematics. You can either use the Lagrange's method of and the grand partition function for finding this. Okay, this I have already discussed. So now let's come to some of the examples. Okay, so this is an example that I wanted to discuss with all of you because you get problems which are very similar to the ones that I would be taking up over here. So in this example, I have basically compared the Maxwell-Boltzmann statistics versus Bose-Einstein statistics versus Fermi-Dirac statistics. So if you come, so the first example is the Maxwell-Boltzmann statistics. So let us look at this. Now, again, if you will recollect what we had discussed about Maxwell-Boltzmann statistics, that the particles are distinguishable, right? And because the particles are distinguishable, therefore, supposing now here what we have done is, we have taken one energy level, two particles, and three degenerate states. All right, one energy level, two particles, and three degenerate states. So I is 1. All right, you're just looking at one single particle, one single energy state, energy level. That energy level has three degenerate states, which is mentioned over here by this 1, 2, and 3, and two particles. Now, in case of Maxwell-Boltzmann statistics, because the two particles are distinguishable, so I've labeled those two particles as A and B. So now let us apply that. If you want to find out the thermodynamic probability, that how many, this thermodynamic probability also gives you the total number of microstates. That is the total number of different ways in which these, so basically two particles, how can they be distributed amongst three different degenerate states, right? So if you use the calculation here from this, so n is 2, gi is okay, so I'm just taking as 1, so g is 3, and this n is 2, so 2 factorial times 3 square upon 2 factorial, right? So you look at this, so 2 factorial times 3 square upon 2 factorial, so this gives you 9. Now let us look at the same situation from the perspective of Bose-Einstein statistics. So again, 2 particles, 3 degenerate energy levels, and 1 single energy level. All right. But here, now what happens is that the particles are indistinguishable. So you can't label them as A and B as we had done in case of Maxwell-Boltzmann statistics. All right. And therefore, if you look at this, whether, see here, so 2 particles in degenerate level, sub-level 1, you can have 2 particles in sub-level 2, you can have 2 particles in sub-level 3. All right. Now, if you look at this, here 1 particle goes into sub-level 1, the other particle goes into sub-level 2. Interchange of these 2 particles will not lead to a new distribution. Unlike Maxwell-Boltzmann distribution, where A in level 1 and B in level 2 was one distribution, and B in level 1 and A in level 2 was another distribution. So here, if you see here, they were 2 different distributions, but here interchange of these 2 particles will not lead to a new distribution. Same over here, interchange of these 2 particles also will not lead to a new distribution, and same over here. So from 9 microstates or thermodynamic probability that was there in case of Maxwell-Boltzmann statistics, here what you see is that there are 6 microstates, or thermodynamic probability is 6. And if you look at the formula for BE statistics, so n is 2, G is 3, so 2 plus 3 is 5, minus 1, 4, so 4 factorial, all right, upon 2 factorial, and 3 minus 1, 2 factorial. So 4 factorial upon 2 factorial into 2 factorial, right? So basically this gives you, so coming back over here, if you look at this, so this gives you 6. And this is exactly what we see over here. Now let us come to the Fermi-Dirac statistics. So in case of Fermi-Dirac statistics, if you, again, 2 particles, 3 degenerate energy levels, but because these are fermions, so 2 things we have to keep in mind. 1, they are indistinguishable, and 2, that they also follow the Pauli's exclusion principle, which means that each of these degenerate sub-level can only accommodate at the maximum 1 particle. So if the 1 particle is over here, the other particle can be either here or here, but you can't have another particle coming over here. So in this case, you see that there are only 3 microstates. And if you look at the formula, so here, so GI is 3, so 3 factorial, N was 2, so 3 factorial divided by 2 factorial, and 3 minus 2 is 1 factorial. So basically, if you look at this calculation, so this gives you 3. So this was, I mean, this is how you actually can, but now this calculation we have done only for one particular energy level, okay? And what we'll also do is slightly later, we'll then discuss a case where we have a number of energy levels, or we fix the total energy of the system, and then you can actually do the same calculation. So that becomes very, very involved. Okay, now this is another illustration that I just took again to discuss the same thing that we were discussing right now. So consider 2 particles and 2 non-degenerate quantum levels 1 and 2. So if I'm saying 2 non-degenerate quantum levels, what does it mean? That there are no sub-levels either in level 1 or in level 2. Okay. Now level 1 is always containing a particle. Okay. Hence, what is the probability that level 2 also contains a particle for each of the 2 cases? When, number 1, when the 2 particles are distinguishable, and 2, when the 2 particles are bosons. Now, and these are the 4 options that are over there. So now let us look at this. neither level 1 nor level 2 have any sublevels. All right. Now, the condition that has been put is that level 1 must always contain at least one particle. So in case, now if the particles are distinguishable, so if I label particle 1 as A, okay, so then what will happen? Level 1 is occupied by A, level 2 is occupied by B. That can be one scenario. Level 1 is occupied by B and level 2 is occupied by A. That can be another scenario. And the third scenario could be that level 1 is occupied by both A and B and level 2 is empty. There could have been another scenario that level 1 could have been empty and level 2 could have been occupied by both A and B, but that scenario we cannot consider because the question clearly says that level 1 always contains a particle. So at least one particle must be there. So that fourth option cannot be considered. So basically there are these three possibilities. So there are three states for such a system, and hence the probability that at least level 2 also contains a particle. So 3 is the total number of different possibilities. Out of these three possibilities, these two possibilities are where level 2 also has a particle. Okay, so the probability is 2 by 3. Now if the two particles are bosons, then you can't label the two particles as A and B. So that is why I've put both of them as A, because then I don't know which is going into which. So one possibility is that one particle occupies level 1, one particle occupies level 2, and the other possibility is that both the particles occupy level 1 and no particle occupies level 2. So if these are the two possibilities, the possibility where at least one particle also occupies level 2 is this. So there are two states for such a system, and hence the probability is 1 by 2, right? Okay. Am I audible?
Yes, Dr. Saxena. Yes.
All right. All right. Okay. So now, okay, fine. Now I'll just, okay, now let me just come on to the final part of my talk. Okay. So in the final part of my talk, this is an example that I was wanting to take. And this is a very good exercise, because if we do this, we'll really understand how this entire distribution works. So first I'm taking the same example for Maxwell-Boltzmann statistics. Then I'll discuss the same example for Bose-Einstein statistics, and finally for Fermi-Dirac statistics. So when I look at the same example for Maxwell-Boltzmann statistics, then let me, now what I'm looking at over here is that my total number of particles is 6. The total energy of the system is 6 epsilon, okay? And this is my energy level with energy 0. This is my energy level with energy 1 epsilon. This is my energy level with energy 2 epsilon. And this is my energy level with energy 3 epsilon. This is my energy level with energy 4 epsilon. This with 5 epsilon, and this with 6 epsilon. And that's why EF by epsilon, I mean, this is the energy level by epsilon. So that's why the numbering 1 to 6. My constraint over here is that the total energy of the system should not exceed 6 epsilon. That is the way I distribute these 6 particles has to be such that the total energy of the system cannot be more than 6 epsilon. All right. Now, and GI, this is the degeneracy. So my degeneracy, so this state also has 3 degenerate sublevels. This state also has 3 degenerate sublevels. This also has 3 degenerate sublevels, and same over here. All right. So degeneracy is 3. Now, for Maxwell-Boltzmann statistics, let us look at the first case. 5 particles are in energy level 0. Okay. So the total energy of the particles in this level will be 0, because 5 times 0 epsilon gives you 0. And one particle is in energy level 6. So this condition is satisfied. because if I add the energy of all these particles, I will still get 6 epsilon, right? I have also distributed all the 6 particles over here, all right? And now the degeneracy is 3, okay? So total number of particles was 6, so 6 factorial times 3 was the degeneracy, so 3 to the power 5, 3 to the power 5 over here, because there are 5 particles in 0 energy level, right? So 3 to the power 5 upon 5 factorial times, there is 1 particle in this energy level, so 3 to the power 1 upon 1 factorial. So the total number of different arrangements that I can have is 18. How 18? Because if you now look at this, there are 3 degenerate levels, sub-levels in this. So this particle can be in either of the 3 levels, right? And for this particle to be in either of the 3 levels, now there are again 3 levels over here. So these 5 particles can also occupy those 3 levels within a particular sub-level. The particles amongst themselves do not lead to a new distribution, but if they are distributed amongst different sub-levels, then they do lead to a new distribution. So for example, if this particle is in sub-level 1 over here, that is one distribution. If it is in sub-level 2, that is another distribution. If this is in sub-level 3, that is another distribution. So in this manner, if you do this calculation, you find out that for this, you get 18 microstates, and this particular distribution represents 1 macrostate. Okay, so this is 1 macrostate, and this has 18. So 18 into 3 to the power 5 microstates associated with it. All right. Now let us look at another distribution. 4 particles are in level 0, 1 particle is in level 1, and then 1 particle is in level 5, right? So this condition is again satisfied. And again, I put the same thing. So 6 factorial times now 3 to the power 4 upon 4 factorial times 3 to the power 1 upon 1 factorial times 3 to the power 1 upon 1. So here my total number of microstates that are present, that I can, or the total number of different distributions in this macro state is 90 times 3 to the power 5. In this manner, you can actually do all these other distributions. I've just taken 2 of these just to illustrate the point, but you can do all these other distribution for each of these. The number is written that how many microstates are associated with each of these. Now this number is this times 3 to the power 5, because it's a huge number. So that 3 to the power 5 factor is common to all of them. So that has been taken separately. So these are the number of microstates associated with each of these macrostate. In all, there are 11 macrostates, and the total number of microstates for this entire system is 1386, which is the sum of all of these times 3 to the power 5. All right. So this was for Maxwell-Boltzmann statistics. Now coming to Bose-Einstein statistics. Okay. Over here, if you look at this, 2 things. One, that the particles are now not distinguishable, but they are indistinguishable. Okay. So if the particles are, so for example, how the particle, what will matter over here, because like there are 5 particles. So what will matter over here is that how the particles are distributed amongst the 3 sub-levels, but within a sub-level, which of the 5 particles have occupied one particular sub-level, that will not lead to a new distribution. Okay. So keeping that in mind, again, the total number of particles is 6. The total energy of the system needs to be 6 epsilon, right? And the degeneracy is 3. So if you look at this, here, what you get is, so again, the same distribution, 5 particles in level 0 and 1 particle in level 6. So here what you have is, so if you look at this level, so 3, that is Gi plus Ni, N is 1. So 3 plus 1 minus 1 factorial upon Ni factorial. So that is 1 factorial times Gi minus 1 factorial. So 3 minus 1 factorial. Okay, so this is for this level times. Now let us look at this level. So here Ni is 5. So 3 plus 5 minus 1 factorial upon Ni factorial. So 5 factorial times 3 minus 1 factorial. Okay, so this, when you solve this, you get 63. Okay, now you look at this. Over here, now this is the second case. So here, this level has one particle. So 3 plus 1 minus 1 upon 1 factorial into 3 minus 1 factorial times this level also has one particle. So again, the same factor again for this level. And then there are 4 particles in level 0. So 3 plus 4 minus 1 upon 4 factorial times 3 minus 1 factorial. This gives you 135. So a similar calculation for Bose-Einstein statistics gives, so these are the total number of accessible microstates for one particular macrostate. So the total number of macrostates is again 11. But the number of microstates for the first one is 63. Whereas over here, if you look at this, this was 18 into 3 to the power 5. So much bigger number. Similarly, for this, the total number of microstates is 135. Whereas over here, if you look at this, this was 90 into 3 to the power 5. So again, much bigger than 135. And if you look at this, the total number of microstates that are available for this entire system is 1532. Whereas if you look at the similar calculation for Maxwell-Boltzmann statistics, it was this huge number. Okay, so what one sees is that the number of even though the number of macrostates is the same, but the number of microstates, the total number of microstates that are associated with the entire system is much less in case of Bose-Einstein statistics than it is in the case of Maxwell-Boltzmann statistics. And now coming to the last example, coming to the last example that I wanted to discuss is the Fermi-Dirac statistics. Now here, what we know is that the particles are not only indistinguishable, they are also following the Pauli's exclusion principle. That means not more than one particle can occupy one sub-state or one sub-level, okay? Everything else remains the same. Total number of particles is 6. The total energy of the system is 6 epsilon. The degeneracy is 3. Now, let us look at the ground state. See, if you look at these two cases, in both these cases, the ground state, we could populate it with 5 particles. Reason being that there was no restriction on the total number of particles that could occupy a particular sub-level. But here, each sub-level can accommodate a maximum of 1 particle. So if you put 3 particles over here, 1 in each of these sub-levels, or one in each of the degenerate energy levels, then in order to get the total of 6 epsilon, so you're left with 3 more particles which you have to accommodate in higher energy levels. So if 1 particle goes to level 4 and 2 particles come to level 1, so 1 plus 1 plus 4 gives you 6. So this total is achieved. And now for this, if you look at the number of microstates, so 3 factorial because GI factorial. So GI factorial, GI was 3. So 3 factorial times. Now let us look at this. Okay. This state. Okay. So if you look at the, just look at this formula. This one, right? So if you look at this formula, so GI factorial upon Ni factorial times GI minus Ni factorial. Okay. So from this formula, if you do this calculation, so there is 1 particle here. So 3 factorial upon 1 factorial times 3 minus 1 factorial. Then this has 2 particles. So 3 factorial upon, sorry, this should have been 2 factorial times 3 minus 2 factorial. So this is actually 2 factorial. So sorry for that slight error. this should have been 2 factorial times 3 minus 2 factorial, this, and this is for this level. And then for this level, 3 factorial upon, because there are 3 particles over here, so 3 factorial times 3 minus 3 factorial. So basically, when you calculate this, you get the total answer as 9. Now let us look at the other second, this macro state. 3 particles in level 1, 1 in level 2, 1 in, so with energy 0, 1 in energy 1, 1 in energy 2, and 1 in 3. So 3 plus 2 plus 1 is again 6. So this condition is satisfied. Total number of particles is also 6. So here again, if you look at it, this level will give you 3 upon 1 factorial, 3 minus 1 factorial. This will also give you the same 3 upon 1 factorial, 3 minus 1 factorial, and this will also give you the same. So these 3 are the same, and then 3 over here. So this factor comes over here. So this gives you 27. So in this manner, now again, you can do this distribution, this. So what you finally see is that in case of Fermi-Dirac statistics, the total number of macro states is 5, whereas in case of both Bose-Einstein statistics and Maxwell-Boltzmann statistics, the total number of macro states was 11. So the number of macro states is also less, and also the total number of microstates of their entire system is only 73. Compare this with Bose-Einstein statistics, which was 1532, or with Maxwell-Boltzmann statistics, which was even still a huge number. So with this, I would like to end here today. Okay, and thank you so much. And now I would like to take the questions.
Dr. Saxena?
Yes, ma'am.
Yes, so I had, first of all, thanks a lot for very briefly but very nicely covering the basics of the classification of quantum and quantum statistics amongst Bose-Einstein and also Fermi-Dirac statistics, and how we choose to distinguish between the two and so on. There were several question answers there. I have answered some basic ones myself, taking the liberty of answering some very basic questions asked by the students. However, you can see in the question answer box some 14 questions still. So could you please take them up? Can you see the question answer box? I'm sure.
Okay, yes. So I think I'll just start. I think the first question was that kindly explain about number density and why its unit is per meter cube, right? Okay, so number density is basically the total number of particles per unit volume. That is how we define the number density. Okay, so typically when you say density, what comes to our mind is that, because we are right now conditioned, our mind is conditioned to thinking about density as mass per unit volume. But in statistics, whenever we talk of density, we typically refer to number density, and in number density, what we are actually referring to is number of particles per unit volume. So at the very beginning of my presentation, that is why I took that example, because this is something that we've been studying since I think class 7th or 8th, that at standard temperature pressure, you have 1 mole of gas occupying 22.4 liters of volume. So 22.4 liters of volume typically converts to 22.4 into 10 power -3 meter cube. So so the total number of particles in 1 mole is Avogadro number 6.023 into 10 power 23. So number density basically means the total number of particles in 1 mole. If I'm specifically talking with respect to 1 mole. So in 1 mole, 6.023 into 10 power 23 atoms, occupying a volume of 22.4 into 10 power -3 meter cube. So the number density would be this number, the Avogadro number, divided by the volume that these particles are occupying. And because the number of particles do not have any units, it's just a number. So the total unit of number density will just come out to be meter inverse cube. So that was the answer to the first question. I hope that answers it. The next question is, how do we visualize the spin of an electron if we consider it as a point particle? Okay. First of all, what I would like to say over here is that this concept of point particle, the moment we talk of quantum mechanics, this concept of point particle actually gets destroyed. It is no longer valid. And that is why we talk of wave particle duality. So what we say is that whereas the particle will interact like a point particle, or it will interact like a particle, but when it is moving, then it will move like a wave. And that is how we try to explain very in a very simple manner. So whenever we are talking of a particle, okay, in quantum mechanics, the way we describe a particle is by the wave function, right? So the wave function basically describes the particle, and the thermal de Broglie wavelength, or the de Broglie wavelength, is the wavelength associated with that particle, which has a particular wave function. So when you're talking of electrons, now please again refer to again my initial slides, where I had said that when does quantum nature become significant, or when is it that we really need to consider the quantum nature. So when I'm saying when we need to consider the quantum nature, what I mean is, when is it that we also need to take into account the wave nature of the particle, right? So when the wave nature of the particle has to be also considered, that is when the quantum mechanics becomes significant. That is when it has to be considered. So the wave nature of the particle has to be taken into account. So the condition that I had mentioned over there was, one, that the wavelength, the de Broglie wavelength, is greater than or equal to the interparticle separation. That is one of the first conditions. Okay. So that, and then the number density times the cube of the de Broglie wavelength should be greater than or equal to 1. So if these two conditions are satisfied, then typically we say that the particle is not a point particle. It can no longer be visualized. I'm not saying it's not a point particle, it's not a point particle in any case, but it can no longer be visualized, because when we say point particle, that is just an approximation, which is a very good approximation, works very well for the macroscopic world, the world where we are living in. But when we talk of particles of the size of an atom or the size of an electron, then this this macroscopic description does not work well. We have some very big failures of classical mechanics and classical statistics. The photoelectric effect is there, then specific heat of metals and all that. So I mean, we have, I'm sure that that is something that would be that would have been covered, or would be covered probably in some of the other topics or lectures. But for here, what I'm just wanting to say is that point particle is something which is no longer valid when we are talking of quantum mechanics. The size of an electron, okay, is typically such that at that scale, at that level, the wavelength associated with the electron is equal to the interparticle, or is approximately same as the interparticle separation. And therefore, the electrons behave as quantum, I mean, they exhibit quantum nature. And because they exhibit quantum nature, therefore, the spin also becomes important. And as far as the spin, particularly the spin part is concerned, the spin actually the spin of the electron is basically, see again, let me just digress a little bit into what I had very briefly touched at the beginning of my presentation, and which was the Heisenberg's uncertainty principle. Actually, what do we understand by the Heisenberg's uncertainty principle? Delta x times delta px is greater than or equal to h cross by 2. Okay. Delta, so if you do this calculation in 3 dimensions, so what do you get? Delta x times delta y times delta z times delta px times delta py times delta pz. This will be greater than or equal to h cross cube by 8. Okay. Delta x times delta y times delta z. this gives you a volume element in spatial coordinates, which defines that you cannot go below this volume element if you want to track a particle. So this is the minimum volume that would be required for a particle to exist, because of the uncertainty principle, you can't shrink it any further. Okay. Now, the other part of the uncertainty principle is delta px times delta py times delta pz. So this, if you again multiply these, see, this gives you the volume element in the momentum space. Okay, that is that this is the minimum volume element in momentum space. You can't specify the momentum of a particle any further. Okay, now arrange these 6 quantities in a slightly different manner. Delta x times delta px, what is this giving us? Delta x times delta px gives us a quantity which is the angular momentum. Okay, what is your angular momentum? R cross p. So the units of angular momentum is length times the momentum. So delta x times delta px gives us the uncertainty in that angular momentum. Okay, and similarly delta y times delta py, and similarly delta z times delta pz. So as a result, what you see is that this, if you take the uncertainty principle and you multiply it along all the 3 dimensions, what you get is that the minimum uncertainty determining the angular momentum of the particle in that volume. Okay, so this volume, which is a product of the spatial coordinate volume plus the momentum space volume, is called your phase space volume. Each of these phase space volumes, so there is a minimum limit that applies to each of these phase space volume, and that minimum limit is h cross cube by 8. All right, this is the minimum limit of phase space volume. Your particle cannot be compressed in any further phase space volume than this. In other words, what I'm trying to say is that h cross, this Planck's constant, is actually that minimum unit in which your quantization of the quantum mechanics happens. I hope you're able to understand from this that your entire quantization, when we say quantum mechanics, what do we mean by quantum mechanics? That there is some quanta, right? You say quanta of energy. What is quanta of energy? You say that in quantum mechanics we write energy as h cross omega. Okay, where omega is the angular frequency and h cross is the Planck's constant. You say that in quantum mechanics we write the momentum of a particle as h cross k, where k is the wave vector and h cross is the Planck's constant. So what is this h cross? This h cross is that quantization. Okay, so the entire quantization of quantum mechanics, when we say that, okay, in classical mechanics the energy levels are discrete, are continuous, and when we move to quantum mechanics the energy levels are discrete. So this discreteness in energy levels, this discreteness in momentum states, how does this come? The discreteness is coming because of that h cross, that Planck's constant. So that quantization of the in the quantum mechanics is because of the Planck's constant. The Planck's constant has units of angular momentum. Okay, and because it has units of angular momentum, so it means that there is some kind of a motion, a rotational motion or a spinning motion that is associated with it, and that is why you get in fact, I think ma'am was also explaining briefly when I was not there, so ma'am was also explaining the same thing, that so for electron, when we say that it has a spin half, it is half h cross. So that spin angular momentum is half h cross. So any angular momentum or any quantization in quantum mechanics is in terms of h cross. And this h cross cube or h cube, this defines the minimum volume in phase space that is required for a particle to be there. Okay. And in statistical mechanics, specifically when you talk of quantum statistical mechanics, this minimum volume of phase space that is required for a particle to exist, this is what you call as 1 microstate. So this unit of volume in phase space is what also defines your microstate in quantum statistical mechanics. So firstly, we can visualize the spin of an electron from quantum mechanical arguments. But for that, considering electron as a point particle, that probably cannot be done. Okay, then the next question was, what is the reason for the occurrence of degenerate energy states, and in what ways does one degenerate state differ from another when both have the same energy? All right. Again, the degeneracy, I'm sure that this is going to be taken up in quantum mechanics part of your these lecture series. Uh, there are different ways in which this degeneracy comes in. But typically, what I just want to say over here is that there are two types of angular momenta that are associated. One is the orbital angular momentum, okay, not just for electrons, but even for protons and neutrons. There are two types of angular momenta. One is the orbital angular momentum, and the other is the spin angular momentum. So if I'm just taking the example of electrons, so if there is a nucleus in the middle, so the electron is moving about the nucleus, right? So this movement around the nucleus, this is due to the orbital angle. I mean, because of this, you have an orbital angular momentum associated with the electron, and then the electron is also spinning. Now here, when I'm saying spinning, it's not that. I mean, you normally say that it's spinning like a top, but it's not typically like that. But it's just that there is another kind of an angular momentum which is associated with it, and which is the spin angular momentum. All right, and so because of these two, angular momentum, and the fact that you can have clockwise and counterclockwise, when you can either go like this or you can go like this, right? Similarly, when you are spinning, you can either spin clockwise or counterclockwise. So in both these orbital angular momentum as well as spin angular momentum, this clockwise and counterclockwise direction gives rise to two different sub-levels for that same energy level, because everything else remains the same except that whether the motion is clockwise or anti-clockwise. That is one reason. Then there are interactions. There are spin orbit interactions. They lead to another kind of degenerate states. And then there are the fine structure and the hyperfine structure interactions. So those lead to a still different kind of degeneracy. So there are a number of ways in which this degeneracy comes about. And so what happens is that you have one energy level. Okay. So what is that energy level? That one energy level that we're talking about, that when you solve the no, okay, so I'm right now only talking about the non-relativistic quantum mechanics. So for solving the non-relativistic quantum mechanics, you generally use the Schrodinger equation. So when you solve the Schrodinger equation, okay, and you do a separation of variables, then you actually get the solutions. So if you are doing, if you're using r theta phi as your, that is the spherical polar coordinate system, if you're using for solving the Schrodinger equation, then the solution for r gives you your principal quantum number, which is your quantization of energy. The solution of theta gives you your orbital angular momentum quantum number, which is quantization of the orbital angular momentum, and your phi gives you your in fact actually spin to aata hi nahi hai, because spin will only come for relativistic quantum mechanics, but orbital angular momentum में ही आपके दो और वो आते हैं. तो एक तो क्या है, एक तो magnitude of
Dr. Saxena,
yes ma'am,
we have students from all over India, so please use only English. There are many people from down south and Assam and so on. Huh?
Right ma'am, right ma'am. So in case of Schrodinger equation, because it's a non-relativistic equation, so the spin part doesn't come, but in the the orbital angular momentum part, there are two aspects to it. One is the magnitude. So the one solution gives you the quantization of the magnitude of the orbital angular momentum, and the other solution gives you the quantization of the direction. One is the quantization of the magnitude and the other is the quantization of the direction. So what happens is that when you do this, so I'm sure you would have done something like this, that total number of degenerates. So if your orbital angular momentum is L, okay, so your total number of degenerate states is L into L plus 1 under the root, right? So that is how you get for the, I mean, this entire thing. Otherwise, I'm sure that in quantum mechanics, this would be covered in greater detail. And so why for the same energy? Because those are the solutions. So for the same energy levels, you get these different states. So that is why they are all sub levels. So in one level, you have those sub levels that are occurring. Okay, then so when this is the next question that I'm going to. So when there is no degeneracy, can we treat Fermi-Dirac and Bose-Einstein statistics as same as per the last illustration? No, not, because of the reason that even if there is no degeneracy, still in one state you can at the max accommodate only one particle. You see, whatever is your energy level available in Fermi-Dirac statistics, you can have one particle only occupying one particular energy level. We say two particles when we take the two spins, spin up and spin down, right? So even if you are taking the spin up and spin down consideration, then also at the maximum two particles. Whereas in case of Bose-Einstein statistics, if you have 10 particles, all the 10 particles can go to the same state, but not in case of Fermi-Dirac statistics, even if there is no degeneracy. Okay, what does zero energy state signify? Won't they have some ground state energy? Yes. Okay, zero energy state, again, for example, if you take the case of a harmonic oscillator, then the zero energy state or the ground state has an energy, because when you find out the solutions, the energy level solutions for a harmonic oscillator problem in quantum mechanics, then the n plus half h cross omega comes out to be the solution, where n is your the states. So if n is 0, which is your ground state, still half h cross omega would be the energy associated even with the ground state. And what we call this is as the 0 point oscillation, that even though we are saying that it's the ground state, so ideally one assumes that the ground state should be 0 energy state, but still there is some energy associated with it because of these 0 point oscillations. And what are these 0 point oscillations? These 0 point oscillations actually come about again because of that uncertainty principle. So there are two forms of the uncertainty principle. One is delta x, delta px is greater than equal to h cross by 2. The other form is in terms of energy and time. Delta E, delta T is greater than equal to h cross by 2. So even in the ground state, for us to be able to find out that what is that minimum energy, there is some uncertainty. You can't go below that in a particular time. Okay, so therefore that restriction because of the uncertainty principle gives us some minimum amount of energy, which we call as the 0 point oscillations. Okay. Now when I'm saying 0 of energy over here, okay, because in the example I took that as 0 of energy, so that 0 of energy simply refers to the 0 energy state. Okay, and that in any case that when you're talking of some finite energy, now when I'm saying some finite energy, what am I referring to over here? I'm referring to some energy in terms of kBt, because we were talking of statistical mechanics. So if I'm referring to the energy in terms of kBt, then epsilon would in terms of kBt, when your epsilon is very small, okay, that is only 0 point oscillations exist, that will be negligible in comparison with the kBt scale. Because today what I had not specifically written in those distribution functions, but maybe which is something which I'll take up next time, is that in the distribution function you have e to the power epsilon by kBt. So when your energy is the ground state energy, then that ground state energy is much smaller than the kBt, and therefore those 0 point oscillation energy. So that is why you can take it as 0. Okay, then the next question is, I couldn't understand GI here. Please explain once again. Okay, GI is the number, is the degeneracy. Degeneracy means the number of sub levels that may exist in a particular level. And like I think I've already explained to you what this degeneracy means, and I'm sure this concept of degeneracy would be taken up in greater detail in your quantum mechanics classes. Sir, what is the relevance of GI equal to 3 in Maxwell-Boltzmann statistics? Okay, GI equal to 3, the relevance over there is that because all the particles are distinguishable, so if you are putting the particles, so long as the particles are in different sublevels, they will constitute different distributions. But supposing if I put particle A and B in the same sublevel, that is in the same degenerate state, then they will not constitute a different distribution, because end of the day the particles are identical. So within a sublevel, because the particles are identical, so amongst themselves they do not constitute a different distribution. But so long as they are placed in different sublevels, they do constitute a different distribution. So if particle A is in sublevel 1 and particle B is in sublevel 2, then, and if I interchange, these are two different distributions. And this is exactly what I'd also mentioned in my slide, and that is what I'd also shown in one of the examples over there. Will the number of macrostates always be the same for Maxwell-Boltzmann and Bose-Einstein systems with same energy restrictions? Okay. The number of macrostates, yes, you can say that, because the way you are distributing the particles, since there is no restriction on the number of particles that can occupy a particular energy level or sub-level. So, okay, number of macrostates, yes, but number of microstates will always be different, because the way these particles are distributed amongst the sub-levels, that will depend upon whether that counting changes from when you're saying that the particle. Sir, in this last example, how three particles can occupy the same state of it follows. No, the particles were not occupying the same state. I specifically mentioned that state, each state has a degeneracy 3 or has 3 degenerate states. So actually one particle was only occupying one degenerate state. So even though in all you had 3 particles in the same energy level, but each particle in itself was in a different degenerate state. Okay. Sir, in FD statistics illustrations, why can't we take the particle up to 6th energy level? Okay. The reason being that if you take one particle in energy level 6, that means the remaining 5 particles have to be accommodated in energy level 0. Now that energy level 0 has 3 degenerate states, each of which can only accommodate a maximum of 1 fermion. So only 3 fermions can be accommodated in the energy level 0. So the remaining fermions have to be accommodated in higher energy level. In fact, this is something very interesting, which we will discuss in the next session, where we'll talk about that when you talk of Fermi-Dirac statistics and you try to put all the particles in the ground state, what happens is that at temperature 0, okay, at temperature T equal to 0 Kelvin, all the particles up to the Fermi energy will be occupied. I mean, all the energy levels up to the Fermi energy will be completely occupied, and all energy levels beyond Fermi energy will not be occupied. So which means that even at temperature T equal to 0, you will still have some energy in the system. But for Bose-Einstein statistics, at T equal to 0, all the particles will condense into a ground state, that is the 0 energy state, or not, I shouldn't say the 0 energy state, but the 0 momentum state. And that is called Bose-Einstein condensation. So that will, in fact, I think then this will become even more clear. Okay, the next question was, at temperature T equal to 0 Kelvin, all particles in ground state. So does this mean Pauli exclusion principle is violated? No, please. This is, I think, the same question as the one before. At T equal to 0, there were 3 degenerate levels. Each degenerate level was only accommodating 1 particle. So the Pauli's exclusion principle was not violated. So from your presentation, can we infer that at absolute 0, fermions will have to be spread over different energy levels since they obey? Yes, definitely. You're absolutely right. So the system should have some energy even at 0 Kelvin. Please clarify. Yes, and like I said, we will take this up in the maybe next session, where I will discuss about the Fermi concept of Fermi energy. So all energy levels up to the Fermi energy are completely filled up even at temperature T equal to 0 Kelvin for fermions. how can a system have different microstates for the same quantum system in Fermi-Dirac and Bose-Einstein? Sorry, Fermi-Dirac and Bose-Einstein statistics. Okay. Okay, different microstates is basically the different number of arrangements in which the particles can occupy a particular macrostate. So what when I'm saying a particle can occupy a particular macrostate, it is that uh, uh, a particular macrostate basically denotes that particular energy level has some specific number of particles. But having said that, with for example, we had looked at that in case of Bose Fermi-Dirac statistics, one macrostate was where the ground state had 3 particles. Level 1 had 1 particle, level 2 had 1 particle, level 3 had 1 particle. Okay, so now the way these are arranged, okay, that distribution, the number of different distributions in which this arrangement can be achieved, this gives you the number of microstates, right? That will be different for both Fermi-Dirac and Bose-Einstein statistics. Simply because that Fermi-Dirac statistics will require you to follow Pauli's exclusion principle, whereas Bose-Einstein statistics will not require you to follow Pauli's exclusion principle. So that is the reason why this will happen. For example, in Fermi-Dirac statistics, when I say that 3 particles are in energy level 0, all the 3 particles are occupying 3 different degenerate states. For Bose-Einstein statistics, when I say that 3 particles are in energy level 0, the 3 particles can be in any one of the 3 degenerate states. Each one of them can occupy 1 degenerate state. 2 of them can be in one and 1 can be in another. So you see, whereas there is only 1 combination for 3 particles with degeneracy 3 occupying the ground state for Fermi-Dirac statistics, but in case of Bose-Einstein statistics, that same number of particles in the same energy level will lead to many more combinations or distributions. And that is why your number of microstates is much higher in Bose-Einstein statistics than Fermi-Dirac statistics. Okay, no, this is not 0. 0 factorial is always 1. 3 minus 3 factorial is 0 factorial, and 0 factorial is 1. So only one thing, how does 3 to the power 5 factor come in Maxwell-Boltzmann distribution? Okay, I have just taken it out. I had taken it out as a common factor because that 3 to the power 5 was occurring in all the calculations. So I took it out as a common factor. And then I just summed up about the remaining terms. That's it. You can simply multiply it also with all the terms that were occurring to get your final numbers. I just taken it out as a common factor. So can you please explain how the Pauli's exclusion principle is obeyed for the distribution of particles in Fermi-Dirac statistics for the last example you gave? Pauli's exclusion principle basically states that no fermion or electron can have all the 4 quantum numbers same. Okay, so basically what it means is that in terms of a quantum state, no 2 fermions can occupy the same quantum state. So when I'm talking of degenerate state, each of these degenerate state represents one unique quantum state. So each of these degenerate states can at the maximum accommodate only 1 fermion. And that is why the Pauli's exclusion principle was not violated, because you had 3 degenerate states and hence you could accommodate 3 fermions in the ground state. How does the knowledge of number of protons, neutrons, and electrons suggest us the proper statistics? What is their connection to the spin of the system? Okay, so proton also has a spin half, neutron also has a spin half, and electron also has a spin half. All the 3 are spin half particles. So if the total number of protons plus neutrons plus electrons is even, then depending upon whether their spins are adding up or cancelling out, you will either get the total spin as 0 or an integer. But if the total number of protons plus total number of neutrons plus total number of electrons is odd, then whether the spins are adding up or they're cancelling each other, finally you will have 1/2 integral spin left If the remaining all cancel out, and if some of them are adding up also, then you will have higher multiple of the half integral spin. How to calculate the trajectory of an atom with respect to a neighboring atom? Okay. With respect to a neighboring atom, actually, this calculation of trajectory of an atom is again, so basically how you calculate is that you use these distribution functions, okay, and then you actually do the velocity distribution. So you can do various types of, so for example, you're using any of the distribution functions, then depending upon what you want to find out from that, accordingly you find out the distribution of that particular quantity. Okay, so it could be the energy distribution, it could be the velocity distribution, it could be the momentum distribution, it could be various types of distribution. So from that you find out, and then you find out the trajectories. But again, in case of trajectory, let me tell you that trajectory can only be found out when you are looking at Maxwell-Boltzmann statistics, or that is for classical systems. In quantum mechanics, finding or tracing the trajectory of individual particles is not possible. So that please keep in mind. What does having lesser microstate or macrostate physically mean? Okay. See, macrostate basically represents a particular, I mean, from the example that I took, it represents a particular distribution of energy where different particles, I mean, the way they are distributed in different energy levels, so that the total energy remains constant, the total number of atoms remains constant, and a particular number of atoms or particles are occupying a particular energy state. Microstate refers to the distribution within a macrostate also, how these particles can be distributed without changing the overall structure of a macrostate. So if you would have seen in the figures that I took, whereas your number of particles for a particular energy level remained the same, but yet the number below, which was representing the number of microstates, was still a big number, or was some number bigger than 1. Okay.
Dr. Saxena,
Yes, ma'am.
you have been speaking continuously for now almost 2 hours plus now. So if there are a large number of questions, we do the following. I pass on the question answers, the questions posed in the question box to you on email, and probably you can take some of them later on or answer some of them on email. Because
Right,
as we can see, I think you are at question, you still have few more questions to go. Or
yes,
if you think you can do it, it's up to you.
Actually, ma'am, because when I
I
started the question answer session, that time there were some 13 questions, and now there are 29 questions. So I guess while the
so
question
you
answer,
can I will just like to read out something which will make you really smile and get some energy. So he's saying that 1 minute, yeah. Was one of the students, Jitin, is saying, sir, imagine all the students attending the webinar following Fermi-Dirac statistics with each sub-level of 2 meters due to COVID and giving you a standing ovation. What a lecture. Thank you, sir. So the students are really, you cannot read chat and question answer at the same time. I'm enjoying all the compliments that you are getting because of your nice and beautiful lecture. And me along with the students are very thankful to you. So you please decide if you would like to take a break of a minute, it's up to you, or if you would like to continue.
I'll just go through these questions quickly and see if there is anything new which I have to say. Then I'll just say. Otherwise, I'll just skip the question. Right?
Okay.
So I think I'll just finish it so that, I mean, these questions are all done. Okay.
It's up to you.
Yes, ma'am. I'll just wrap it up, ma'am. I think in another 5-10 minutes I'll wrap it up.
Yeah. For us, it's not a problem. Just for you, I was asking.
Ji, ma'am. Then the one is, we do not consider the interaction of particles while studying statistical mechanics. Hence, there will be error. How do we consider these errors? Are there any further extensions to statistical theory? Yes, you're absolutely correct. When we study statistical mechanics, to begin with, we say that the particles are non-interacting. Interactions, when we consider interactions, then actually there are modifications and there are changes that have to be done. So this is a more involved topic. So for the time being, I think for in the context in which we are discussing this, we will have to stick to that the particles are non-interacting for all types of statistics that we are considering. Sir, what is the difference between H and H cross? Oh, okay, so there is no difference as such. H is actually the Planck's constant. H cross is simply H by 2 pi. And the reason why H cross is normally used is because when you're talking of energy, so either you can write as H mu, where mu is the angular frequency, now, or you can write it as, so mu is the frequency, H mu, where mu is the frequency, or you can write as H cross mu, where H cross omega, where omega is the angular frequency. So that depending upon how you are defining your frequency, whether you're using mu only, then you use H. If you're using omega, which is 2 pi times mu, then you use H cross, that is H by 2 pi, so that your overall factor remains the same. Okay, then sir, as you just said, again, how do we define the orbital angular momentum when the electron doesn't have a defined trajectory around the nucleus? It does not have a defined trajectory, but like I said, there is something what you call as the quantization of the direction. So there are fixed directions and it chooses one amongst those fixed directions for it to orbit around the nucleus. So yes, there is no one single trajectory. I mean, that can also be there, but that depends upon what is your value of L. Okay, that depends upon that. So if L is 0, because for n equal to 1, L can be 0, and so on. I mean, that again, quantum mechanics, you would have done that. But if L is 0, then you would have only one quantized direction. If L is 1, then you will have 3. If L is 2, then you will have 7. And if L is 2, so 2 into 2, 5. You will have 5 quantized directions. So in that sense, you can have those trajectories which are there. So will electron gas also show classical behavior at high temperature and low density? Yes, but that will have to, you will have to see that what will be the temperature, how high will that temperature be. So that one has to see. And at that high temperature, will the density be, can you keep the density low? That's a big question. Because like for example, you studied neutron stars, that's another example of Fermi-Dirac statistics. So they're also extremely high temperatures, but again, electron density is also high. Please recommend books to get started with statistical mechanics and also up level. I think there is Reef, Statistical Mechanics by Reef. Then there is Sears and Salinger. Then there is Kersen Huang. There is R.K. Patria. I mean, I think these are some of the standard textbooks that you can refer to. Why our first concern is to determine the energy? How can we use to determine other parameters? Here we are actually using the energy as the, for the discussion that we've just had, we've used energy as the basic parameter, and probably we'll continue to do that. But if I'm talking of quantum statistics, or not quantum statistics, but quantum mechanics actually, then the more fundamental quantity to look at is the momentum. That is the more fundamental quantity to look at. Books I've already said. The thermal de Broglie wavelength you have discussed hold good only in semi-classical limit. Am I correct? The thermal de Broglie wavelength holds good only in semi-classical limit. Well, the thermal de Broglie wavelength actually defines the wavelength of a particle at a particular temperature. That is the wavelength associated with a particle at a particular temperature. What probably you want to say is, in case of Bose-Einstein statistics, when you go to the, you get the condensation happens. That is where the statistics breaks down, and all the particles go into the ground state. So that, what happens then? So okay, at the transition, yes, the thermal de Broglie wavelength becomes very large, and then ideally it extends up to infinity, and that is why all the particles condense into a ground state. and they become a condensate. That is, they behave in completely the same manner. So can two particles be in the same degenerate level in FD as I saw two particles? No, the two particles were not in the same degenerate level. They were in two different degenerate level. Each energy level had 3 degenerate levels. So the particles were in different levels. That is why the maximum number of particles was always 3. It was never more than 3 in any particular level. So can you once again explain the need to divide quantum statistics further into Bose-Einstein Fermi-Dirac? Okay, the need is basically dependent upon the choice of the total spin of the particle. If the total spin of the particle is 0 or integral, then you have to use Bose-Einstein statistics. And if the total spin of the particle is half integral, then you have to use Fermi-Dirac statistics. The reason is simply because for Bose-Einstein statistics, that is for 0 or integral spins, the Pauli's exclusion principle is not valid. So you can populate one particular energy level with any number of bosons. Whereas in case of Fermi-Dirac statistics, in case of fermions, the Pauli's exclusion principle is valid. So you cannot go on populating any one particular energy level with fermions. You have to follow the Pauli's exclusion principle. Why are atoms with more neutrons less understood? Okay, this is, I think, question from quantum mechanics, and not even quantum mechanics. I think high energy physics. So I think beyond the scope of this lecture, at least. Sir, can you once again explain the need to divide? Okay, that I've already taken. I think, ma'am, that finishes off all the questions. So
yes, it's been really 2 hours that we have been speaking about statistical mechanics and associated concepts. So I'm really thankful to you, Dr. Aditya Saxena. And your lecture has only proven that when I do feel that such and such lecturer or such and such professor of the university should be invited to give a lecture series to the students, I am absolutely correct in my choice. So your compliments are innumerable, and I will forward them to you for your reading. I think it is really very nice that your consistent way of telling the statistical mechanics details to the students has made them really love physics. They are writing that we are so we are feeling so joyful that through this lecture we have started loving statistical mechanics, which was earlier a little bit scary to us. Well, actually, that is it. I mean, when some student says it is a scary subject, it's a difficult subject, I feel a little bit awkward because I think statistical mechanics is, except for the few equations which you have to manage, otherwise it is something you can remember all your life without having to, ever open a book or something. And I'm sure in the coming sessions, the students will enjoy it a lot. So I thank you very much, along with my co-convener, Dr. Pushpa Bindal, and the panelists and the organizing team.
thank you so much, ma'am. And
thank
it's
you so
really a
much.
pleasure that you people have invited me and given me this opportunity to interact with students. So I'm
Yes.
really grateful for that
Thank you, Dr.
opportunity.
Saxena. Thank you. It was really a very good talk, and it was equally loved by the students as well. We are thankful that you spared your precious time for this. Thank you.
Welcome, ma'am. Welcome.
Okay.
Okay.
Thank you so much, sir. So we will
Welcome, ma'am.
meet again in the following sessions of statistical mechanics.
Yes, ma'am.
Okay.
Okay.
Thank
Bye.
you.
Good night. Good night to all the students.
Yes, good night to all of them.